This is a binary stiffness compliant mechanism that can be triggered using a single bistable switch to achieve two different states of stiffness with two translational degrees of freedom. When the mechanism's red switch is positioned outward as shown here, its white stage is stiffly constrained to not move in any direction. But when the bistable switch is triggered inward, the stage can freely translate with minimal stiffness, but only along the directions that are perpendicular to this dashed line as depicted by a disk of black translation arrows shown here. Although this disk contains an infinite number of translation arrows, only two of them are independent, and thus the mechanism is said to achieve 2 degrees of freedom. In this way, the mechanism switch can be triggered in and back out again to repeatedly achieve 2 states of low and high stiffness respectively along multiple degrees of freedom. To understand how the mechanism works, it's important to first understand its compliant topology. The mechanism is made of 16 parts that are assembled as shown here. Its flexible elements are categorized into 3 types: flexure bearings, tuning springs, and bistable switch elements. The flexure bearings, colored orange, consist of 3 axisymmetric limbs of serially stacked pairs of parallel blade flexures. Alone, the flexure bearings permit the mechanism stage to freely translate with the 2 desired degrees of freedom while stiffly constraining all other unwanted directions. The tuning springs, colored yellow, consist of angled wire flexures that lie on parallel planes. 3 pairs of these parallel planes of wire flexures are arranged in an axisymmetric way to directly join the mechanism stage to its bistable switch. The bistable switch elements, colored red, consist of 3 axisymmetric sets of parallel but angled flexible elements that join the switch to the mechanism's fixed ground. When the bistable switch is oriented outward as shown, the wire flexures of the tuning springs are straight and thus stiffly constrain the mechanism stage so that it can't move in any direction. When, however, the mechanism's bistable switch is triggered inward so that its flexible elements stably remain angled up, even after the triggering force is removed, the wire flexures of the tuning springs buckle and curve outward as shown. Note that the wire flexures are all fabricated with a slight curvature to begin with, so that when they buckle, they do so in a controlled way. Once the wire flexures are appreciably curved after buckling, they fail to provide any constraint to the mechanism stage, and thus the stage achieves the 2 translational degrees of freedom of the flexure bearings. In this way, the position of the switch alters the constraining nature of the tuning springs to effectively turn the mechanism's translational degrees of freedom on and off. But altering the nature of flexible constraints is not the only factor that enables the mechanism to achieve large changes in stiffness. The mechanism also leverages the principle of stiffness cancellation. To understand this principle, consider first this simple schematic of a stage joined to a linear spring, colored orange, with a stiffness kT1 of 1 Newton per centimeter. Suppose the stage is constrained by rollers such that it can only translate in a single direction with a displacement of d. The force displacement plot that would result from loading the system stage with a force F kT1 would be the orange line plotted according to this equation. Now consider removing the orange spring and attaching a different linear spring colored yellow to the stage with an undeformed length LT of 20 centimeters and a stiffness KT2 of 3 newtons per centimeter as shown here. If the new spring is preloaded by displacing its fixed end inward and amount delta T equal to 5 centimeters, and the stage is only allowed to translate in the direction perpendicular to the preload with a displacement of d, the system's force displacement plot that would result from loading the stage with a force FKT2 would be the yellow line plotted according to this equation. If the same preloaded spring scenario is then repeated, but the orange spring is added back to the system in parallel, the system's force displacement plot that would result from loading the stage with a force F would be the blue line plotted according to the sum of the previous two equations. Note that when the positive stiffness of the orange spring is summed with the negative stiffness of the preloaded yellow spring, the stiffnesses cancel and the system exhibits a region of near zero stiffness. If the preload is removed from the yellow spring, i.e. delta T is set to 0 centimeters, the resulting force displacement plot would be the purple line plotted here. Note that the instantaneous stiffness of the system, i.e. the derivative of the system's force displacement plot at d equals 0 centimeters with the preload, where delta T equals 5 centimeters, is 0 newtons per centimeter, but the instantaneous stiffness of the same system without the preload, where delta T equals 0 centimeters, is 1 newton per centimeter. Thus, by displacing the grounded end of the yellow spring inward, the stiffness of the system can theoretically be reduced by a factor of infinity. For practical systems, however, an infinite reduction is not possible since no real system can ever achieve a perfectly zero stiffness. Nonetheless, this example demonstrates how dramatically the principle of stiffness cancellation can reduce the high stiffness state of a binary stiffness system to a low stiffness state by simply preloading a spring. Note that although the dimensions and stiffness values given in the schematic example do not correspond with the real mechanism, the positive stiffness orange spring and the negative stiffness yellow spring shown in the schematic example are analogous to the orange flexure bearings and the yellow tuning springs of the real mechanism respectively. The red bistable switch of the real mechanism can be triggered in and out to displace the yellow tuning spring's grounded end to reduce and increase the mechanism's stiffness similar to the schematic example. The number and kind of unique parts that constitute the fabricated mechanism are shown here. The parts were all 3D printed and assembled together using small bolts. An Instron testing machine was used to experimentally characterize the mechanism's performance, first along its x-axis translational direction. With its switch oriented outward, i.e. configured in its stiff state, the mechanism was fixtured in the Instron's clamps and was stretched and compressed over 3 cycles as shown by this force displacement plot. Note from how well each cycle traced the previous cycle's contour that despite being made of a polymer, the mechanism exhibited impressively low hysteresis. The mechanism's switch was then triggered inward, and in the resulting compliant state, the mechanism was again stretched and compressed over 3 cycles as shown by this force displacement plot. The force displacement plots of the third cycle, measured from both the stiff and compliant states, were plotted together as shown here to enable a clear comparison of the stiffness change between both states. The stiffness, i.e. the slope of the force displacement plot of the stiff state, is 6.5 newtons per millimeter, and the stiffness of the compliant state is 0.56 newtons per millimeter. These measured values demonstrate an impressive 91.4% decrease in stiffness. The mechanism's switch was then popped back out and then triggered back in again to measure 3 more cycles of the second trial of the compliant state. The third cycle of both compliant trials is provided in this force displacement plot. Although the wire flexures of the mechanism's tuning springs were observed to occasionally buckle differently each time their switches were triggered inward, this plot demonstrates that the mechanism is sufficiently repeatable for practical applications. Similar force displacement plots were generated by loading the same mechanism rotated 90 degrees along its y-axis translational direction. These plots show the results of the mechanism being loaded over 3 cycles in its stiff and then compliant state. This plot shows the third cycle measured from both the stiff and compliant states plotted together. The stiffness of the stiff and compliant states are 6.87 newtons per millimeter and 0.49 newtons per millimeter respectively. These measured values demonstrate a 92.9% decrease in stiffness. The plot showing the third cycle of the mechanism loaded over 2 different compliant trials is shown here to demonstrate the mechanism's switch repeatability along the y-axis. The stiffness values of the mechanism's orange flexure bearings alone, measured along its x and y axes, was 0.71 newtons per millimeter and 0.63 newtons per millimeter respectively. Note that these values are greater than the measured stiffness of the full mechanism triggered in its compliant state along its x and y axes, i.e. 0.56 newtons per millimeter and 0.49 newtons per millimeter respectively. Thus, these results validate the presence of stiffness cancellation in the mechanism. If you want to learn more about how this mechanism works, be sure to read our paper published in the Journal of Composite Materials. A link to the paper is provided in the description below. Additionally, the mechanism's part files can be downloaded on Thingiverse using the link also provided in the description. Finally, I wish to thank my graduate students, Sam Shimohara, for optimizing, fabricating, and testing the mechanism, and Ryan Lee for providing advice and technical support with the project. Thanks for watching The Facts of Mechanical Design.